You raised your hand. You think you're the laziest person in the room? If you really are, the person next to you will be raising the hand for you, right? Well, so what about being lazy? Why should we talk about being lazy? Remember what our parents kept telling us? Don't be lazy. Get out of the bed. Go get the work done. Well, you know what? They are right. They always are right. Parents are always right. But when it comes to code execution, it's actually a benefit to not being eager. Now, one of the practices we follow in agile development is the so-called thing called last responsible moment. Well, that last responsible moment can apply for the code that executes as well. So what does it really mean to be lazy? It really means you don't do certain computations until you no longer can avoid doing the computations. And when you do have to do the computations, you do that only minimally. So in other words, when you are looking at having to process a high volume of data, and when you're talking about high frequency of data, and also creating an application that is very, very responsive, you can try to really attain the responsiveness by trying to run things very, very fast. But at some point you will realize there is only so much you can do really fast, but by changing things around a little bit, you can be more efficient by not running faster, but by running much more efficiently, meaning I'll only do enough of what I should really do. In a way, you could think about this as the rule of what to do when you're chased by a bear. When you're chased by a bear, you don't have to be the fastest person to run. You only have to run faster than the guy behind you, right? So that's where the smartness comes in, right? So you think about how can I really become more efficient by executing enough code but not a lot of code in a faster manner. Well, let's talk about being lazy for a minute. Laziness is something we all are familiar with at various levels. But I want to start with something called the order of execution. There is the so-called applicative order, and there is this thing called normal order. Most of us, I would say almost everybody in this room, potentially, we all have only used applicative order because that's what is available in most of the mainstream languages. And the word applicative order, just like the word, what it means, the order of evaluation of a function is in the order that you apply it, meaning replace the word apply with invoking it. So the minute you invoke a function, it runs. That's called applicative order. So let's take a look at an example of this to get a feel for it. It'll be very obvious when you look at this because we see this all the time. So I have a function here. Let's say in this case I'm going to say add. And this function takes a and b in this case. And of course I'm going to say, let's just for our purpose, let's say add called. Let's say that. And then I'm going to say in here, return a plus b. Then I have a function, let's say, called evaluate. It takes a value and it returns, let's say, the value. That's all it does, right? Not very useful. But then I'm going to go ahead and call this function. And the function I'm going to call here is called evaluate. And the evaluate function says add 1 and 2. So I'm going to run this code, and you can see what it did. It said add called, and then it printed 3. But the question is, when did it call the add function? It called the add function first, isn't it? Once it called the add function, it took the result of the add function, sent it to the evaluate. So if I go here and say evaluate called, notice that it will call print evaluate called only after it printed add called. You're probably sitting there and thinking, duh, that's the way it works, right? Why are we even talking about it? Well, that's called applicative order. And that's the way things work. Not because that's the way it should work. It's because that's the way it has worked. That's one thing we need to always keep in mind. Not everything we see is the way the world should be. It's just that the way the world is. So this is called applicative order because you first apply the add function and then take the results of add and you send it to evaluate. Now let's take a look at this a little differently. I'm going to go into the evaluate function here, and I'm going to return a 42. Now, what do you think is going to happen when I run this code? What will it do first? It'll call add. But then what will it do with the result of add? Nothing. Throw it away. Isn't that a waste? That is eager evaluation. The minute you give it, it's like, oh my gosh, you gave me a function, I got to run it. It never looked around and said, what are you doing with the result? Oh, you're not even using it. Why should I waste my time running a function when you least care about the value of that function, right? So in this example, when I run this code, you will notice in this particular case, it actually runs it and then throws it away, isn't it? Am I making sense? Let's try this one more time. I'm going to go back here, do the same code, add AB equals A plus B. Evaluate value equals value. Am I writing the same equivalent code here? Absolutely right. Then I say main equals do, print, and in this case I'm going to say evaluate, and I'll say add 1 and 2. So it prints the value of the result, in this particular case 3, absolutely. But just to see that it's actually doing it, that was Haskell code, so I'm going to go ahead and bring up the Haskell REPL. I'm going to load this code here, and I'm going to say sample.hs, and I've loaded this particular code into my REPL, and I'm going to set a breakpoint. And the breakpoint I'm going to set on line number 1, but in this case I'm going to set it at column number 16, which is where that code ends. So that there you go. I call the main function. Notice it is waiting in that function because it stepped into it, right? Absolutely. Then I say continue, and you can see that it printed the value 3, as you would expect. However, I go back to this code now and say return 42. Haskell says, wait a second, you are calling all this function. It looks at add 1, 2. It says, oh, you want me to call add 1, 2? I'll get back to it. It's very lazy. It then says, oh, you want to run evaluate? I'll get back to it. Then it goes to print. Oh, you want me to print something? Oh, that I cannot avoid because you want to see the result now. Now it says, because I have to print, I'm going to run the evaluate. It goes into the evaluate, and the evaluate says, take this value, and Haskell says, I'll get back to it. What do you want to do with it? Throw it away and return a 42. And Haskell says, sure. Then that means I don't have to ever run the add method. That is laziness, right? So if you notice in this example, now that I made this change, let's go back to the code again. I'm going to load the function one more time. I'm going to set the breakpoint exactly there one more time. I'm going to run the main function this time. Notice it never stepped into that function. Do you see that? Because that's absolutely lazy. This is called normal order. The word normal doesn't come even close to saying what it really is. It is actually quite abnormal because we don't see it in many places, right? Most of the languages we use do applicative order. Most languages we program do not do normal order. But normal order is phenomenally powerful because it says, I'm going to do only work where it really matters. If it doesn't matter, I would not do it, right? Here's one example. One of the things I have to do every year, I got to file the stupid tax return. The tax return is due on the 15th of April. And at 11 p.m., 15th of April, I sit down in front of God and say, dear God, if I'm going to live for another hour, let me know now. I'll file that stupid tax return. I mean, if you're going to die, why would you want to waste your time filing tax return, right? And so that is the main point is you postpone until the last responsible moment. Okay, now I can no longer avoid it. Next morning, if I have not filed it, the IRS comes behind me. I better get this out of my way, right? So that is basically the laziness. You don't do it until it really matters. Well, you may say, well, is that a really good thing? It is actually a very good thing because whenever you do something, there's two things happening. You're doing that, but you're also taking time and resource away from something else that could be done. By being lazy, you're only focusing on what's important. And by postponing it, you got two benefits. You do it when it's very important, and if it is not needed, you saved all the time and effort because you never bothered to run it. Now imagine the add was a very expensive function, where it's going to take a lot of time to compute. And the compiler says, I didn't really take any time running it because you never used the result for it, right? So that is an example of laziness, and that has been baked into it. But you already saw this. Some languages are born lazy. They're just phenomenally lazy, right? It's like the parents saying, I knew it from the day he was born. That's the way he looked, right? Such a lazy bum, right? Well, that's kind of these languages, right? They kind of sit on the beach and they kind of look around and they do absolutely nothing, right? And they have a good time. Some languages are naturally lazy, as you just saw. Haskell is fundamentally lazy. You don't have to do anything. Other languages have to work really hard to be lazy. It's kind of like me, right? My wife would say, why don't you just sit there for a minute and do nothing? I'm like, that's hard. Do you understand that, right? And so some of us have to really work very hard to be lazy. And so are languages, right? You got to really say, well, let's be lazy here. Let's take a look at an example of this. So look at this a little differently for a minute. We know this concept of short-circuiting quite a bit, right? So let's go back to this example here. And let's say we have this add method for a minute. And let's say here we're going to have a value. Let's say int value equals, let's say 5. And I'm going to say if value is greater than, let's say 6, and let's say add of 1 comma 2 is equal to, let's say 3, I want to do something here. Let's say result, whatever that computation is, right? Else, let's say no result. So in this particular case, when I run this, that's pretty beautiful, isn't it? What do you call this kind of behavior? What is the name you use for this? Where the if does part of it but not the other part? Short-circuiting, right? Short-circuiting. A technical term for this is called the McCarthy. That's one of the features that implemented this was Lisp, and it was created by McCarthy. So McCarthy short-circuiting, absolutely that works, very nice optimization. However, I'm going to take this add from here, and I'm going to say, let's call this as, sum, and I'm going to say int sum equals that. Now when I run, what's going to happen? It'll run the add. Not fair, isn't it? If it was really smart, what will it say? Oh, you created sum, but you're never using it, so I'll postpone running this add. So if this add was taking a little bit of time, then you wouldn't waste your time running it because you never use the result, right? What if we can do something like that? So let's take a look at another example here. So this example here, I'm going to write in Scala just to entertain this thought. So let's say here is a value v equals 5, just like the way I did a minute ago. And I'm going to define add. Let's say a is an integer and b is an integer also. And within this, I'm going to simply say output, and we will say add called. So here is add called. And now what I'm going to do here is I'm going to simply say, now that I have that function, if v is greater than 6 and add, let's say 1 comma 2 is equal to 3, and I'm going to say output, let's say result over here, else let's say no result. Very similar to what we did, right, a minute ago in the case of Java. So I say no result. So in this case, of course, when I run this code, you can see it is not going to run the add function because there's no reason to run the add function literally in this particular case. So it's not going to run. And then when it is giving the result, you can see it simply prints no result, just like in Java. However, I'm going to now say sum, and I'm going to say val sum equals add of 1 and 2. Now notice when I run, what did it do? Did exactly what Java did. Pretty sad, isn't it? However, you can tell Scala a little bit and say, come on, Scala, work a little hard, be lazy. So when you tell it to be lazy, it no longer evaluates it. So you can prod the language a little bit and say, just don't be so eager to run that function. Just be a little lazy. So notice now it became a little smart and said, I'm going to wait until you actually use some. If you never use some, I won't bother running it. So notice now, the behavior is not like in Java. The behavior is a lot like it's in Haskell, right? So we had to work a little extra hard in this case. And of course, if you said, if it is less than 6, you can see add was called, because that's when the sum is being used. But if you said greater than 6, because sum is no longer needed, it never evaluates it. So we could become lazy by saying we want to be lazy. That's another thought. We had to work just a little extra hard. But of course, in Java, we have to work a lot more harder than this, right? So how do we really make Java lazy? We talked about why you want to be lazy. The reason you want to be lazy is by postponing operations until the point you absolutely need, you get the benefit of not even running it if you don't really need it, and that's definitely a benefit. But how do you really be lazy in Java? Well, Java employs applicative order. Java will never use normal order. So how could we, in a world which is using applicative order, how could we really become lazy? Well, the trick to that is to use lambda expressions. How does this help? Well, a guy named David West once said, in computer science, we can solve almost any problem by using a level of indirection. And this is a phenomenal thought, right? We solve so many problems by using a level of indirection. And laziness is a level of indirection. Rather than doing the work, you delegate the job to something else that does the work. If you take this to several levels, where instead of you doing the work, you give it to somebody else, who in turn gives it to somebody else, that is called the government, right? Eventually, it's absolute laziness. Nothing gets done. But maybe you don't have to go that far, right? So the point is, you can keep postponing it by using a level of indirection. So how do you really make this work through a level of indirection? Well, that's exactly what Java can do with lambdas. So let's get back to this Java code and see what we can do. I've got this sum over here, as you can see, and it is doing it eagerly. As you saw, it evaluates it. But what I can do is I can say, well, this is after all a function, so I'm going to bring in a function in here. So function.function. So now I can define a function, takes an integer and returns an integer, and we will call it as sum equals, and given a value, right? Well, actually, in this particular case, it wants two values to be given, A and B, but that's okay. We can even change it to something even better. We'll call it supplier. That would be even easier. So let's say here is A equals 1, this is B equals 2, and I'm going to change this to a supplier, and the supplier is going to give us an integer in return, is equal to, it simply says I want to return A plus B. That's, well, actually, let's go ahead and call the add method. Add A plus B, right? So we could even do this. In this case, of course, 1 and 2 is what I really wanted to use, so we don't even need this. So we just have a supplier, and what did we apply right on line number 11? We applied a level of indirection, isn't it? Rather than doing the job yourself, you gave the job of doing it to another function, right? So you said, hey, do this. Okay. And you say, do this. So you just hand it off to another one, said, you do it when I'm asking you to do it. Well, that's a level of indirection. Now, the add function is sitting right here. Now I can say here, sum.get is equal to 3. So I could move this to one other level of indirection. Notice this time, it never ran that. But if I said if v is less than 6, you can see it is running it. But if it's greater than 6, it's no longer running it. So you're kind of introducing the laziness by saying, I will move this into a lambda, and then whenever I invoke the lambda, it'll run it, but not otherwise. You can take this and twist it multiple levels now. You can now say, hey, instead of you giving me a value, I'm going to accept a lambda instead. So let's kind of see how this is going to play out. So notice, I'm going to go to the evaluate function. So public, let's say static, int evaluate, remember that function, int value, and what did it do? It said return value, remember? And in this case, of course, I'm going to come down here and say, well, I'm going to call this function, and I'm going to simply say, call the evaluate. So here I could say evaluate, and I could send to this, for example, add 1, 2, and I could send this. And in this case, it called the add function. But what if I don't use the value and send a 42? You can see that it still did the hard work. Let's rewrite this for a minute. Rather than sending the value, go ahead and send a supplier. And the supplier says, I will give you an integer when you ask for it, right? So we'll call this as source or whatever you want to call it. Now here I'm going to say source.get. So now when I go ahead and run this code, you would notice it is going to call this method after all because we are returning the result. However, if I go back and say return 42, notice that function is never getting called at this point, and even though we are done here. And the reason for that, of course, is you received the source, but you never used it. So we are slowly moving towards simulating the behavior of normal order within the realm of the applicative order. So the moral of the story is, if you want to become lazy in Java, start receiving lambdas rather than receiving values. Because a lambda is evaluated at compile time, but executed at runtime. And you can decide whether you want to execute it or simply postpone it, right? So that gives you a bit of a laziness on your hand pretty effectively. Well, let's take this to the next level. That's nice, but how could we really become even more lazy? Well, to become more lazy, we would have to rely upon streams. Java 8 streams are fundamentally lazy. When you tell them, call methods on it and say, do some work, they actually don't do the work until they really have to execute the work. So to understand this, let's take a look at one example here as to how we will do this. So let's start with a little example of a set of values to work with. So the values I want to start here with, I'm going to say here is list of 10 numbers here for me. So I have a list of 1, 2, 3. Notice it's a 5, and then I'm going to say 4, and that order. So notice the order is 1, 2, 3, 5, 4, 6, 7, 8, 9, and 10. Given this order of list, find the double of the first even number greater than 3. Let's do this in the imperative style we are already used to. So we would say int the result equal to 0, and we want to output the result when we are done. We'd say for element, int element, in coming from the numbers. And what would you do in this case? You would say if element is greater than 3 and element mod 2 is equal to 0, well then result is equal to element times 2, and then you would break out of it. Well, that gives us the result 6. This is an imperative coding style that we are all used to. But we can do a lot better than this in a very nice declarative manner. Output, and I'm going to say in this case, given the numbers get me a stream, first perform a filter operation where, given an element, get me an element greater than 3. Once more perform a filter given an element, give me an element which is even number, then perform a map operation given an element times 2, but go ahead and give me the first only, find first, and once you find it, get me that result. So you can see it produces exactly the same result here as well. But the difference is, this is a lot more declarative. But if you look at this through your naked eye, you may look at this and say, oh my gosh, this is stupid. Because you're going to do so much work, and what a waste, isn't it? Imagine for a minute, I've got 1,000,000 elements. If I have 1,000,000 elements, line 18 would first take 1,000,000 elements, assuming this is done in a very naive manner. What will it do? It'll take 1,000,000 elements, and it will give me a collection of all the values greater than 3. Let's assume that's still close to 1,000,000, right? Maybe 1,000,000 minus a few. Then it finds all the even numbers. That will still be a very large collection. Then it doubles all the values. That's still a very large collection. Only to take the very first one, right? So this is really absurd because you did a lot of work to throw away most of the result. Well, thankfully, that's not the way it is going to do. In fact, let's look at what's going to really happen. They both produce the same result, but what's the complexity of the operation? I want you to closely look at this for a minute. Look at the fact that the array contains 1, 2, 3, 5, 4, and 6, 7, 8, 9, and 10. So first of all, let's count the number of operations. Line number 10, is 1 greater than 3? No. It's a short circuit. It will never go any further, right? Is 2 greater than 3? No. Is 3 greater than 3? Is 5 greater than 3? Oh, yes, it is. Is 5 even? No. Is 4 greater than 3? Is 4 even? Double the value 4, break. How much was it? Total. 8 computations, right? That's exactly what it took, 8 computations. So this efficiency of this was, or the need for this was 8. Now let's get back to the code in the bottom. If this is done naively, this would become, taking a 10 elements, it would filter, checking every single value is greater than 3. How many operations is that? 10. Dead on arrival, isn't it? 10 is greater than 8. But let's add insult to injury a little bit further. Continue. Well, it takes all these values now, 7 values, and checks if they are even. How many is that? Total of 17. 4 more results left. Double the 4 values. 17 plus 4, 21. 8 versus 21, what do you think? Absurd, right? You wouldn't want to do this. But thankfully, this is not the case. The streams, I've noticed, share a characteristics I've only noticed among my children. They both are lazy to the bone. My children sit there and keep fighting, and I say, are you done with your homework? Oh, yes, Daddy. How did it go? Wonderful. Do you have any problems? Nope, everything works fine. Let me take a look at it. Sure, and they disappear. And that's when they start working on it, right? So it feels that way. So you go to the stream on line 8 and say, hey, stream, yeah, filter, done. Filter again, done. Map, done. Find first, oh dear, we got to do some real work now. But they do it minimally, right? So if you notice, let's do a quick refactoring here to see this. I want to go back to this code and say, change this to sample is greater than 3. Change this one to sample, and I'm going to say is even, and change this one to sample, double it. Now let's go ahead and say public, and let's say static int, boolean rather, is greater than 3, int number, and here I'm going to say return, let's say number greater than 3. Likewise, we'll add 2 more functions. This is even, and I'm going to simply say mod 2 is equal to 0. And this is going to be a value int, we'll call it as double it, and this is going to simply return number times 2, producing the same result as it did before, no difference. However, I'm going to go back here and say output, and output what I want to output in this particular case. I will say, well, I want this one to be is greater than 3, I will say plus number. Likewise, I will print out here is even, and I will print here double it. Now if you notice, if you go back and run this code, notice the number of operations it performed. Exactly 8 operations. It never even touched the values beyond the value of 4. So how does this work? So in other words, what it does is, it doesn't do any of those until the value really matters. And when the value matters, it runs through vertically doing enough work. So here is a nice way to think about it. Imagine these are your 2 feet. You're standing up there. Imagine you're standing there and you're looking down. You first take the number 1 and you drop it. What happens to number 1? it comes to line number 9, and it says, oops, 1 is not greater than 3, and it runs the sideway out. You're like, oh, we lost 1, let's try 2. 2, 3 do the same thing. What about 5? 5 clears line number 9, but escapes through line number 10. Then you say, well, those are complete waste. Let's try 4. And what does 4 do? 4 clears line 8, line 9, line 10, line 11, and hits line number 12. And you hear this tongue, hey, wait, it went really, reach the bottom, we're done. Because we found the first one we are looking for. And it never bothers to run anything more. In fact, if you really look at this for a minute, suppose I were to remove this from here for a second, and let's just stop with the get, and I'm going to simply say output over here. Let's simply say done. Now when I run this code, you can see it did all that work, and it said done. But the trigger is actually this function here. So if I comment out the last 2 things and put a semicolon right here, even though I'm calling all those functions, notice it never actually ran any one of them because it's absolutely lazy. So it got together and said, look, nobody cares about the result. There is no reason to run. This reminds me of an experience. I had a developer in a conference ask me, she said, my boss wants me to write reports endlessly. This is a waste of my time. I'm keep writing reports, and I'm tired. And I said, what does your boss do with your reports? She said, well, I go every Monday, give him the report. He takes my report and files it. I said, I got an idea for you. Mistakes can happen. Take a bunch of random papers from the next week, staple them together, that's your report. And her eyes brightened and said, thanks. That's exactly what I'll do because I know he will never ever read it. Why are we writing reports when nobody reads it, right? They don't want a report, they want some random papers, right? That's being efficient. You can go get some real work done at this point. So that's kind of like, you know what, if they never ask for the result, why bother running it? So it completely eliminated that, and as a result, we didn't do any work. But when it does have to do the work, you can see it only does minimum work that's needed, and you got efficiency through it. So that is about laziness using streams. But we can continue with this a little bit further. I'm going to show you 3 more examples of this, so we can get a feel for how we can use this to advantage. Let's say we are interested in working with a collection of people. So in this example, I'm going to create a bunch of people. So here is my create people method. And I've created a bunch of people with different age and different gender and names and gender and age. So list of person, we'll call it people equals create person, create people. But let's define a problem we want to use. I want to say find the first person with a 4-letter name, male, and older than, let's say, 20. So I'm saying find the first person with a 4-letter name, a male older than 20. I don't want to do a lot of work in this case. How many people do I have in this particular case? Well, I've got this 1, 2, 3, 4, and I'll have 8 people in this collection. But I don't want to do a lot of work in this case. So how would I actually write this code? I'm going to say output, and I'm going to start out by saying, oh, let's say people, and dot stream, and I'm going to call a filter. And the filter says, given a person, give me a person's name, so person dot get name, but I'm interested in a person with 4 letters, so dot length is equal to 4, right? So we are applying the filter operation saying, only give me people who have 4 letters long name, not anybody else. Then I'm going to say, filter again, I want a person where the person's gender is equal to gender.male, and then one more filter, isn't it? Filter one more time, given a person, person.getAge is greater than 20. And finally, I'm going to say find first to get the very first person that's available in that particular collection. So that's our execution in this case. It said that's Paul, who is 32 years old. Where in the world is Paul? Paul is right about here. What that means is I would not definitely want to waste my time evaluating Jack or this other Jack or this Jill. However, if my problem changes to a female greater than 20, I would be looking at one of these two, Sarah, well, actually, second Sarah, I would never want to come below that. So how do we know this is actually efficient? Well, let's go ahead and try a few things first of all. Let's go to the person class to begin with. In the get name, let's go ahead and put a little print so we can actually take a look at it. Output called, and let's simply say the name. So if you run this code, you can notice in this case, it never touched Jack, any of those Jacks, as you can see. It stops right there and says, I'm done with my work. I'm going to do only enough work. That's the first thing, right? Second, if you never called the find first still, and if you terminated at the end of the filter, you will notice in this particular case, it never actually evaluates those functions because we haven't asked it to get the result in the very end. So we haven't terminated this. It says, I don't have to really run it, and it postpones all that work until you eventually call a terminal function. So that gives us the benefit of saying, I can avoid doing work until that work becomes very useful. This leads to something even more interesting. We can now, because we have laziness, laziness can prompt us to a few other things we could actually use. For example, an infinite series. An infinite series is a series which has absolutely no bounds. You can start with the value and you can keep on going with the value as many times as you want to, because the generation happens when you request for the data, not when you say I want the series. Once you get a hang of infinite series, you then start conceptualizing problems as an infinite series problems. It's amazing when your thought process changes from, I got to do this imperatively to, oh, I can step back and think about this problem more holistically, and now I can think about how I can go through a series of transformations on an infinite series. It just changes the way you perceive things. For example, I wanted to implement tail call optimization in Java. Well, Java doesn't have tail call optimization. Tail call optimization is where you take a recursion, but you quietly turn it into an iteration so it can be very efficient. Well, Java doesn't have tail call optimization, but I wanted to implement tail call optimization, so I was struggling with it for about 3 or 4 days, and I couldn't really figure out how to do it. And the solutions I wrote were really clumsy. It had mutability in it. It was hard to explain, and I really, after about 3 days, I said, I don't think I'm going to be able to solve this problem. So I decided to kind of take a break and said, I'm going to leave this away, I'll come back to it. And the next morning, I was completely away doing something else, and my brain was slowly thinking about this problem, and suddenly I realized, oh, wait a second, I can conceptualize a tail call optimization as an infinite series problem. How is it an infinite series problem? Well, a recursion, what does it do? You call a function, and it makes a decision whether to terminate the recursion or call another function. What does the other function do if it calls another function? It again decides whether to terminate or call another function. And how far do you go? Well, I don't know. You keep going until you don't want to go anymore. Well, that becomes your infinite series, isn't it? And the minute that thought occurred to me, all that 3 days of wasted effort thrown, within about 15 minutes, I had a wonderful, beautiful, concise code in place. It's very easy to conceptualize problems this way. So let's take a look at an example of how you could do a sequence through this. So what I'm going to do here is to say, I want to create a collection, but it's an infinite collection. So I'm going to start with the stream, and the stream is going to come from, of course, the stream package. So I will say stream. And what am I going to do with this particular stream here? I'm going to tell the stream, I want you to start with an initial value, Well, let's say this initial value, I'm going to say iterate, and that's going to be, let's say, a 1. Then I could say, give me a number e, and I'll give you a e plus 1. Now, just look at that for a minute. If you notice, we already saw this earlier, right? If you give a value or an expression, it's going to evaluate it right now. But if you give a lambda, it can postpone evaluating the lambda. So the second parameter here is a lambda. And the lambda says, if you give me a value e, I will give you the next value in the series. But of course, if you keep doing this, you will eventually run out because it will be an infinite series. But the beauty is you're going to be lazy about it. You're not going to call this at all until you definitely need the value. So now I can say, for example, filter, and I could say, given an element, I want only even numbers. So I could only extract even numbers from this infinite series. Then I could say, one more time, perform a map operation, where given an element, double the value. Well, that's a double of all the even numbers. But how many do you want? Limit this to only 100 values. Then perform a reduction operation, so reduce, and I want this to be an integer, let's say integer, sum. So what we have done in this particular case is, we have written code using an infinite series, where the infinite series keeps producing result only when you ask on demand. You only extract even numbers from it. You double the even numbers, but up to 100 value, and you total it. Now you can start thinking about your problems as where data could be coming as a stream of data, but you don't care how much data you get. You only care about how many data you want, but you are beginning to postpone operations. So once you start thinking about stream of data, it changes the way we perceive things. Let's entertain this thought with a little bit of how this could become efficient. This code should be fairly easy for us to understand. Let's say for a minute you are creating a library of code. Now remember some of the things we learned. We learned about creating modular code. We learned about creating small functions. We learned about creating reusable code. We learned about all of these things. So what do you typically do? You start creating functions for doing stuff. Have you ever written a function that takes a list? Absolutely. Have you ever written a function that returns a list? Absolutely. That's exactly what I've done here. So I have a little function here called stock fetch. And if you look at the stock fetch, it takes fetch stock prices. It takes a list of symbols. And what does it do? It returns a list of symbols. And the code is extremely simple, isn't it? What does it do? Creates an empty array of list. It then goes through one at a time, gets the stock price, puts it into the list, and it returns it. Now, just look at this code for a minute. Can you think about what's wrong with this code? Don't tell me the solution. Listen to the question. What is wrong? Because that's the problem most of the time. We want to give solutions to problems we don't understand. So what's the problem? That's a question. What's the problem in this case? We are saying, yep, go ahead. It is not lazy, right? It says, I am going to give you a list. Well, let's put it in different words about not being lazy. Let's put it in different words. It said, I'm going to give you a list. I don't care what you're going to do with it. That is the most important observation here, right? I don't care what you're going to do with it. I am going to give you a list. That is kind of silly, isn't it? Because that's like saying, I'm going to do all this work. I don't care what you need this for. But what do you normally do efficiently? When somebody comes to you and says, do you have this? Most likely you would ask them, what do you really want? What are you looking for? So don't give me the implementation, give me the problem you're having. Then I will decide whether I should do this implementation or not. So most of the code we have been writing makes a preemptive strike. We are assuming you want the data, I'll give you the data. But it's time for us to ask, what are you really going to do with this data? Why should I produce the data when I have no clue what you're going to do with the data? Now let's define a problem. What are we going to do with this problem? Let me define a problem, what I really want here. And the problem I want here is, given a list of symbols, get me the symbol stock with price greater than 100 and less than 200. Also do the same for 1,000 and 2,000. So what am I saying here? I'm saying, given a list of stock prices, a list of stock symbols, get me the stock price for something that's greater than $100 and less than 200. And again do the same thing for me for something that's greater than 1,000 and less than 2,000. Now we know what the problem is, but we also know one more thing. That may not be the problem all the time. You could be giving me a completely different problem tomorrow, or you could have multiple problems to solve at the same time. But what did the code do? It preemptively said, I don't care what you're doing, I'm going to give you a list. That's pretty preemptive, right? So what can we do? He said we could give an enumerable. Well, think about what we have done in the past. If I'm going to return an enumerable, how do you really implement the enumerable? You're going to start creating an enumerator inside that code. And when you do it, how do you feel about it? Is it a code that's simple enough? Is that code going to be as sweet as the code we just wrote a few minutes ago? Right? If with all that effort, if the code you're going to write is as simple as this one, you probably would do it. But if you're using enumerator, would it look like this? No, it would look like a monster. That may be the last code you write on that project, and then you quit, right? It's like, I can't handle this anymore, right? So the question here is, we want to return something that can produce the result later, but not right now. So let's see how we can do this. Let's use this and see where it takes us, first of all. So timeIt.code, and I'm going to code this using the traditional, I'll call it find eager, how about that? And 100 and 200. Let's go ahead and try this. I'm going to say public, static, void, find eager. It's going to say low and high, and this is not doing anything. It shouldn't take a whole lot of time to do nothing. Now what do I do here? I'm going to say list stock info, and I'm going to say stocks equals, and stock fetch, so that's a fetcher, dot, and what's the function we called? It's called find stock prices. And then what am I going to send to it? Well, tickers dot symbols, and I'm going to send the symbols to it. Once I got it, I'll say stock info, match equals null, because it's possible I don't have a value. And then for, and I would say stock info, and I would say stock, and that comes from the stocks. And what would you do here? You would say if the stock price is less than, what is the value, low, and if it is stock price is greater than, so less than the high, right? So greater than the low and less than the high, then what do you want to do? You want to say, oh, we got a value here, so match is equal to the stock that you just got on hand, and then you would break out of it. And then when you come back in the very end, what are you going to do? You're going to say, finally, well, if match is not equal to null, I'm going to simply output the match we got. Otherwise, I'm going to simply say else output, sorry, no match. So that would be the code we're going to write, isn't it? So I'm running the code. I'm going to ask him for those two prices, one for 100 and one for 1,000. Now, what is the code doing? It's trying to go to the web, find all the stock prices, get the values for us, and give us those results. And notice 14 seconds later, it tells us it is IBM at $170 price among the ticker symbols I gave it. But what's going to happen if I try to run this one more time, and this time for 1,000 and for 2,000? Well, remember, a value has to be greater than 1,000 and less than 2,000. So I don't know what the stock market is doing today. I got about 20 stock prices to work with. And so 14 seconds later, it gives me the value. In the other case, 14 seconds later, if the value is there, it'll give me, otherwise it'll say no match. But that's an eager evaluation, right? We went through all that burden to do the work. Let's think about redesigning this API to make this a lot more efficient once this is completed. So right there, about 14 seconds later, right, each. So we took a total of 28 seconds to do this work. The second one, sorry, no match. No stock prices greater than 1,000 in that list I had. And of course, in this case, IBM was $170, which is within the range that I provided. Let's try this one more time. Let me go back here and say, well, rather than doing this, let's go ahead and say time it one more time. So time it dot code, and in this case, I'm going to say, well, call this as a find lazy with 100 and 200. And again, I'll do the same thing for 1,000 and 2,000 as well. So very similar to the call we are making in here. However, let's go ahead and implement the find lazy. So void find lazy, this takes a low and a high, just like the other solution. But what am I going to do within here? Well, the very first thing I'm going to do here is, I'm going to say stock fetcher dot, and remember we called this find stock prices. Well, I'm going to now call find stock prices lazy, and I'm going to send to it a tickers dot symbols dot stream. So I'm going to pass a stream to it rather than passing a list. Now it is going to return a stream over to me, and what am I going to do with it? I'm going to say filter, and I'm going to say given a stock, give me a stock whose price is less than or greater than the low. Then I tell him, one more time filter, a stock where the stock's price is less than the high. Then find first. And then once you find it, perform a map. Where you have a stock, I'm going to say stock.toString, and or else, if you couldn't find it, I will simply say, sorry, no match. And that becomes my response that I'm going to print out. So let's go back and take a look at what this code is doing. So output that. So what is this saying? It says, given a list of ticker symbols, go get me the values for all the prices. So let me make sure I've covered this properly. So this is going to be ending here. So this should be or else, and that comes from, okay, I think we're good. So I'm saying, go get all the stock prices. That one ends right there, right? That's the stock prices we have from here. Once you get all the stock prices, stream of that, get me the only the ones that are higher than the low and less than the high. Get me the first one, and then perform a transformation because I may not have a result. If you have a result, give me the result itself. If not, I'll just return a sorry, no match. Well, but what about the code? Stock find price lazy. I still have to work on that, isn't it? Let's go ahead and try that. So public static, this is going to become the stream of string, we'll call it symbols. So I'm passing in a symbols over here for him to work with, right? So it's a stream I'm going to take as a parameter. I could have taken a list, but once we are going towards a stream, it's a benefit not to commit to that particular implementation. So I'm going to take in a stream. Once I take in a stream, what should I do? I should return a stream, after all, of a stock info from here. So what's the difference between these two calls now? The only difference between these two calls is the top one is returning a list and taking a list. The bottom one is taking a stream and returning a stream, right? That's the only difference we made in the interface level. So rather than working with a list and returning a list, receive a stream and return a stream, in other words, you're saying fundamentally I'm going to be lazy from now on. I won't do any real work until I really have to do it. So then what are we doing here? Well, okay, you've given me a symbols, and what should I do with the symbols? I'm going to perform a map, and I'm going to say stock util dot get price on the map, and I'm going to simply return that particular result. The code is almost trivial, isn't it? A lot less code to write than we had in the previous case. Because you're saying, I don't have to do real work anymore. All I have to do is just tie these together and say, I'm done. Right? When you ask for it, I'll give it to you, not otherwise. So this says, when you give me a list of symbols, I'm going to simply map those symbols to the price returned, but I'm going to do it very lazily. I'll do it on demand. If you never ask for it, I would never do it. So the first thing, when you call stock price, the first method, the minute you call it, what does it do? It runs off and comes back after and says, there was a lot of work, too much traffic. You call the second one, what does it do? No worries, we can take care of it. Well, how much work did it do? Not a squat, right? It didn't do any work at all when you call it. It says, I will do the work when you ask for the result, not right now. So it completely postpones it, isn't it? So now let's get back to seeing how this is going to work. So this is calling it for 100 and 200 and 1000. Let's first run it only for 100 and 200, and then we will come back and see how it works for the other one. Well, first of all, I need a stream here, so let's bring in a stream that's needed. So this code is going to go through the stream and use it. So in this case, line 14, let me fix this error right here. Oh, where's the error coming from? Error is coming from line number 14 in stock fetcher. Let's fix that one. So public static, not a stock. There we go. So let's try that again. So what is it doing? It says, I'm going to go get the stock price for you. And how much time did it take? 3 seconds. How much did it take before? 14 seconds. Why did it take less time? Why did it take less time? Because it was lazy. It said, I don't have to do as much work. I only need to do minimum work. The minute you get a result, I can go home. I don't have to do all the work to get you the result. Right? We wrote less code and we were lazy at the same time. Of course, it has to do all the work if it couldn't find the result, isn't it? So look at the second case. The second case it has to go through all of them, right? Because it has to come back and say, I'm sorry, I really worked through and I couldn't find the result. And it's a little grumpy. Why? It said I was not able to be that lazy now. I had to, after all, do the work. And then it says, but I'm still happy because I waited until I really cannot avoid it, right? So that is the beauty in this case. That still took the time. Again, 17 versus 14, that could be a network delay. But the point really in this case is, it does have to do quite a bit of work in the end, but that's the worst case scenario. So in the worst case scenario, you have to do all the work. In the best case, you don't. And even in the worst case, you do it only when it's needed. And that's determined at the runtime. You don't do it preemptively ahead of time, right? So that gives you the benefit. So in other words, when you look at reactive systems, for example, when you look at reactive programming, it really starts from here. It's really a combination of using function composition and lazy evaluation and saying, I'm going to have a stream of data coming in, but I'm going to be very lazy in evaluating it, and I will postpone evaluating it until I no longer can postpone it, and I will only do minimum work. So the moral of the story here is, we've been doing too much work, but efficiency can be attained not just by doing things faster, but by sometimes avoiding the work that shouldn't be done in the first place. And so laziness is all about smartly avoiding work that you don't have to do, and then only doing minimum work, but when it is imminent, when it's important, to produce that result. I hope you found that useful. That's all I have. Thanks.